Hello, and welcome to my presentation on WHOIS methodology for classifying assessment items. I'm Dr. Darryl Chamberlain. I'm an assistant professor in the Department of Mathematics, Science, and Technology, and my research focus is in educational data science. So I am trying to extract and make data-driven decisions in the field of education fairly broadly. My work normally is more in the STEM ed field, usually within like the mathematics and statistics specifically. This work is done in collaboration with two colleagues at Georgia State University, Dr. Russell Jeter and Dr. Kelvin Rozier. And so I am going to present just some preliminary results that we have on trying to get a handle on assessments. So assessment, if we think about it kind of broadly, we can think of it as assessment as learning, assessment of learning, and assessment for learning. This is a little different than the summative and formative assessment that people might be used to, but it's this idea that assessment can be used as the tool to learn. So say students doing a homework assignment are learning as they do this assessment. It can be of learning, so like a final exam where we're trying to figure out what did you learn over this course of so many weeks. And it could be for learning. This idea that as an instructor, I want to figure out, well, what do my students know so that I can provide a next lecture, so that I can provide resources for them. And that's where this kind of trichotomy comes from. And if we're thinking about it in terms of that formative assessment, where it's informing the instructor, the as learning and for learning both fit in there, whereas the summative assessment fits very snugly with of learning. And I do want to be careful that these are not disjoint. We might have an assignment that is partially teaching the students as they do it, but also is like a capstone presentation of what they've learned. Like if they were doing a project at the end of a term, doing that project might give them some knowledge of, say, how to do such a project, but it's also a way to provide evidence that they've learned some specific material over the term. So assessment, kind of broad. How do we assess assessments? How do we figure out what's a good assessment, a bad assessment? What does that even mean? There are kind of two schools of thought here, where we have large-scale assessment, which heavily looks at the psychometrics, whereas classroom assessment is more about learning goals. So classroom assessment is usually the small scale. It's more about what do students know, what do they not know, and how can we be sure of what the students know and don't know. Whereas for large scale assessment, it's normally about trying to compare different groups that aren't necessarily in the same place, thinking like standardized testing, where we want to give an exam across the entire nation and compare students that are in a bunch of different places. So these fields kind of clash a little bit in that their goals aren't exactly the same, their concerns aren't exactly the same. And so what we want to do is try to figure out how can we meet in the middle? How can we apply some of the large scale assessment metrics into the classroom so that we can try to get a handle of how do we evaluate classroom assessment? And so that's our goal with this project. Very large goal, so we'll continue to break it down and we won't go into everything that we're doing for that in this presentation. So to get started, we pulled some measures that are in the large scale assessment literature. For this presentation, we're just going to be focused on item level measures. So items are like a single question on some assessment. And again, when we're talking about assessment, we're talking about it broadly. These don't just mean exams. They could be homework assignments. They could be clicker questions if you're doing traditional in-person. They could be just anything that you are using to try to understand what students understand. So you might be familiar with some of these item level metrics or measures. item difficulty, point by zero correlation, maybe not. This infit and outfit, probably not. And effective distractors, maybe you've heard this term, maybe you haven't. But when we have multiple choice assessment, the options that aren't correct are normally referred to as distractors, or things that are plausible but not right. And we can get into that more later. So you've probably seen some of these before, and we can actually pull almost all of these if you're using Canvas Classic, the quizzes. If you were building your quizzes in Canvas, you have access to basically all of these measures. So we thought this was a great place to start to get a handle on this, because what is a good correct student ratio? How many students do we want getting this question right? I mean, in an ideal world, maybe all of them. But is that a good assessment? That's the kind of questions that we're trying to dig into. So we want to know, how do measures of validity, reliability, and knowledge, which was that intersection between the classroom and large-scale assessment, how do these relate to the evaluation of an assessment item? Okay, so going back, our first goal is going to be to classify each measure. All right, we want to be able to say this is a good item difficulty or a bad item difficulty. We want to be able to say this is good or bad for all of these measures. So we're going to need to do some work. And content warning, it's going to require some heavy math at some points. So let's get started with the easiest one, item difficulty. So this is just the proportion of students that got a question right. So between 0 to 1. From a classic perspective, ideally, we'd like this to be about halfway between a random guess and 100%. So if this is a free response, like a homework question, the chances of getting it right are effectively 0 if we're just guessing, more often than not. So ideally, those item difficulties, we'd like to be like 50, right? 50%. For multiple choice, this is going to go up based on the number of options that you have. So 4 options, about 74%, and 5 options, about 70%. Now, this might be concerning. This is concerning if you are a classroom instructor and you're worried about grades. And you could say, well, I don't want all of my questions to be about that difficult. And these are the kinds of tensions that we're trying to figure out and incorporate into how we evaluate these items. So the other thing that we want to talk about and be very careful about is, in the classroom, we normally want questions associated to every learning objective, regardless of how difficult or easy it is. So we need to also take that into consideration. Whereas in large-scale assessment, that isn't a concern. What we really want in large-scale assessment is the ability to differentiate between high-performing and low-performing students. So we do want these ideal item difficulties. We want the difficulties to be around about 0.74, let's say, for 4-option multiple choice questions. So we'll consider that. And we'll say a good question is within 1 standard deviation of ideal, acceptable within 2 standard deviations, and poor is going to be outside that range. And this one is a little bit looser because, as you'll see, item difficulty is kind of a broad thing, and based on your goals for the course, what is good or not can really fluctuate. So let's keep going with maybe better measures of an assessment item. Just for completeness sake, we do want to think about item difficulty distribution. So in an ideal world, all of the questions are in that difficulty range, but maybe some of them are harder, some of them are easier, and then some of them are right in that middle. And we can even look and plot these distributions. And from a classical perspective, we'd like the difficulties to be normally distributed, and we don't want it to be too tall or too short in that curve. So it's this idea that I have a lot of difficulties that are all around that ideal difficulty. But again, in the classroom, that's not something that we really care about. And in fact, it's not very common for educational items to be normally distributed with their item difficulty. So that's a problem. We'll need to figure out a way around that if we want to keep with this idea of trying to incorporate predictiveness into the classroom assessments, right? We want to know if a student does answer this question right or wrong, what does that tell us about their knowledge? And we want that to be consistent across terms, across students. So in terms of this distribution, we can look at this, but again, this is more about looking at the assessment as a total, so we won't dig too deeply into this. But this idea about normality is important and is going to come up later. So point by zero correlation, this is our first time we're getting something that looks a little mathematically complicated. It's the idea that I have some one question on the total assessment, and I want to know what is the correlation between getting that one question right and then the final score. And so it's this idea that, yeah, all of the questions are kind of contributing to the final score. They're all, again, giving that predictiveness about what's going to happen for the totality. And how to actually calculate it, it's a little challenging. Basically, you can see we're comparing the score against averages for the single question and then all of the other questions. That's what this y is. And we're taking this average. Okay, so the correlation squared is determination or variance. And that's measuring the proportion of variation that can be attributed to that variable. So our squared, we'd like that to describe some amount of variation in the scores. And what we could say is, well, okay, if all of the questions are independent, whether a student knows something, it's going to change for each of these questions. The amount of variation that should be explained with a question should be 1 over how many questions there are. And so, for example, if there are 4 questions, I would like the amount of variation, I'd like 25% of the variation be associated to question 1, and then 25% associated to question 2, and then the same and the same, that gives me the full total. So that idea about independence, which is normally violated in the small scale and in the classroom settings where we're trying to build on topics, this at least gives us a starting point to try to have a measure and say whether it's good or bad. The other issue is in the large scale assessments, we only want to include items that differentiate, where again, small scale classroom, we want to include all of the items associated to these learning objectives. So you can hear this tension again and again and again. What is the goal of the assessment? What are we trying to do? And that's going to impact how we make these decisions. So if we thought the last one was a little confusing, this one is even more so because we have 2 variables that we need to attend to. So we have K, which is the number of items on the assessment, and we have N, which is the number of students taking that assessment. So we get this idea of, well, what should the correlations be? Well, we can transform all of these correlations into a normal distribution. This is what the Fisher-Z transformation is doing. And we can determine what the error is in this process when we're trying to figure out what is that true correlation for each of the items. So that gives us one value. And then we have that 1 over square root of k from trying to explain the variation for each item that we'd like to see. And that's what these ranges are doing. So you can see 1 over square root k and this 2 over square root n minus 3. You can see they flip just because at a certain point, comparing n and k, one of these might be bigger than the others, and that's what this is doing. And then we have this weirdness at the end where basically as the number of students increases, the number of students that we have take this assessment, the standard error is going to drop. So we'll be more confident about what the true correlation for an item is. The problem is, as n increases, this goes to 0. And so we lose the poor category. We won't be able to actually make this distinction. So in order to keep that distinction going, we do this subtraction here. Now, the mathematics of what's going on, does this still help? There's a confidence interval being built into the background. End of day, we at least have some very clear boundaries, depending on the sizes of n and k, that we can make a good, acceptable, and poor rating. This also actually kind of matches what is in the literature. So the literature doesn't care about what the size of the assessment is and what the number of students. It just says bigger than 0.15 is good. It'd be ideal if it was more than 0.2. And with our system, this 0.2 bound comes up when k is greater than 24. So thinking like a final exam in a math or physics or chemistry course, this is pretty common. It also happens when n is greater than or equal to 103. So maybe a very large lecture hall kind of class, or the number of students in all of the sections for one course in one term. So we can see here, we built this to try to capture both the very small scale, like one class with 15 students, all the way to a lecture hall with 300 students. And then also a small assessment, 3 or 4 questions, versus a large assessment, like 25 questions. And we wanted to make sure these bounds made sense. And so this is really important if we think about that 1 over square root of k. If k is 2, right? This is just a clicker question. They're just 2 quick questions, or maybe they're 2 questions in an asynchronous video that the students are watching. We want the variation to be 50% for each of those. And these 0.15, 0.20, that's not a good bound because the assessment is so small. So that's why we needed to really massage these point by zero correlations to get mathematically rigorous bounds for judging them. Finally, we can talk about the reliability between the assessments. This is really important when we have multiple versions of an assessment. So again, like a final exam or exams that are cross terms, we can calculate this. This is really important for a large-scale assessment, so we wanted to include it. In classroom assessments, we don't always do that though, right? For homework assessments, for projects, this doesn't really make sense. So it's something we will include sometimes, but again, it'll be more for the big picture total assessment and not the individual items. So we do have bounds for that from the literature, but we'll keep going because that's not a major goal of how we're going to assess our items. Okay, so we talked about normality being important. We talked about being able to distinguish between high-performing and low-performing students. This is something we absolutely want in large-scale assessment. It's something that we kind of want in small-scale classroom settings as well. We like grades on an assessment to distinguish between high-performing and low-performing students. And this doesn't need to be in terms of thinking about penalties and final grade in the course. If we can distinguish between a high-performing and low-performing student, we can provide more resources, targeted resources, to that low-performing student so that their final grade in the course would be what we were hoping. So in order to do this, we're going to rely on logistic curves. So this is commonly used in classification models when we're trying to predict a binary response. Think, if I'm trying to figure out if an email that came into my email box is spam or not. These are the kinds of models that you might use. So this model is taking 2 variables, this student's ability and the item difficulty, and it's trying to predict what is the probability a student would get it correct. So you can hear that binary response. And you can kind of hear how this is a predictive model. So we had a measure for item difficulty. That's pretty easy. How are we going to measure the student's ability? And that is really where this model all comes to a head. So it's this idea that in measuring the student's overall grade, we lose the importance of each individual question and how the student performed in relation to the rest of the students on that question. That is being captured and is what the essence of the student's latent ability or their ability score is. So they'll have one ability score for the assessment, and then there will be an item difficulty for each item, for each question. This is the easy version of the model, though, because more often than not in STEM classes, we have multiple choice. And so is there truly ever a probability of a student getting a question at 0% on a multiple choice? Not usually. And so we can modify this and scale it up to be what the guess probability is. So if they have a 25% chance of guessing it right, a four option question, then this scale just gets squished up to where the bottom is 25% now. So you can see this, we're getting really into some heavy math. And the nice thing about this, though, is it's going to give us a really strong way to discriminate between high-performing and low-performing students. Again, not necessarily to punish the low-performing, but to provide them resources. We really want to know how are they doing, right? Because again, at the end of the day, classroom assessment is all about trying to get a handle of what students know and what they don't know. So you can see here I've bolded estimated. Well, what does that mean? Well, we can't know what a student's ability is to just provide a score. We don't have that kind of omniscience. And how are we figuring out difficulty? Well, we can estimate it based on what some sample does. But as we get more and more values, this number might change. So this is what we mean by estimated. It's going to be based on how students perform in some sample. How we actually do this calculation is a little long, but it's this idea that we are taking these scores and we're standardizing them. We're going to calculate the probability that a student is going to get this question right, and then we will look at how far off we are from that score. So basically, did they get it right or wrong? And then what did the model say was going to happen? And we can slightly modify these two variables in very, very careful ways so that we maximize our model. Basically, we're trying to figure out which of those curves best fit the sampling that we had. That's a lot, though, and this is not a high-level data science presentation, so we'll kind of just breeze over it, but know that there is this classification that's going on in the background. So once we do this, once we have these scores and item difficulties, we can actually figure out, well, what are the things that don't fit the model? So there are two ways something could not fit the model. There's outfit. So if a student has an ability score of, say, 1, and the item difficulty is 1, then that student basically has a coin toss to get it right, the 50% probability. So as the student's ability increases beyond the item difficulty, the student's more and more likely to get the question right. And that's what those curves were doing in the background. So outfit is trying to figure out, okay, well, if these scores are very far apart, if a student's ability is, say, a 3, and this question is like a difficulty of 0 or 0.1, these are really far apart. Our model says that students should get it right every time, basically every time. But does that actually happen? That's what the outfit is trying to detect. And then the infit would be the the opposite, where if the student is really close to the difficulty score, right, what's supposed to be a coin toss, is that what we're seeing? Is it basically a coin toss for the students that are at that stage, or are students getting the question right more than they should based on their abilities? So you can hear that this is, again, a little difficult, but the nice thing is these measures give us a nice way to just do a fit check, the infit and the outfit. And the ways that we measure these are in the literature, mathematically sound. We don't need to do too much work for it, which is kind of nice. Okay, so we've pulled a lot from large scale assessment, but we also want to think about things that are more in the small scale in the classroom setting. And what we'd like to focus on is the patterns of student thinking. So I had mentioned distractors as those incorrect but plausible options. But if it's not a multiple choice, we could still see patterns of student thought. We could still see patterns of ways that students respond. And rather than just say those are distractors, what we're going to say is these are our true patterns. And there could be two types of patterns. There could be incomplete rules or some kind of conceptual thing that is driving it. So this is a way that a student would consistently provide this alternative answer versus a mistake, right? Like, I'm tired. I drop a negative sign. I'm tired. I didn't see the square root, or my thinking is blurry, right? So these are two different patterns that we could see, and we need to tease out when and where they would happen. So for example, one of the most common patterns of student thinking in algebra is something that even has a name. It's called the freshman's dream, where x plus y, all of this squared is equal to x squared plus y squared. And if you've taught math courses, you've seen this all over the place. If you haven't, you might think, well, I mean, this seems reasonable, but if we distribute, there should be a middle term, this 2xy. So the question is this a mistake? Is it a misconception, or is it true? Which it is true sometimes in higher level math cases. But this is probably what the student is thinking, right? It's probably either a mistake or a misconception. So how do we figure out which? What we can do is we can cluster students' responses over multiple questions to try to get these patterns of thought. So if we're thinking, a student might make a mistake, but if they're making a consistent pattern of this way of thinking, then this is probably a misconception, not a mistake. And it's not really a distractor. This is some way that they're thinking. And if we can detect that, we can respond to it, right? We can provide resources to try to change their thinking. So the idea of an effective distractor, or maybe a pattern of student thinking that's not just randomness. In the literature, we see that as it's this type of response more than 5% of the time. So we have to be really careful about that. Is 5% actually the best? We might need to negotiate that. So for example, if I asked, what year was the first multiple choice assessment used, and I gave these options, you would immediately throw away 2025. I mean, you have seen multiple choice assessments before this year. So that one, likely not to be effective. But what about the others? Do you think a student would choose 973, 1451, 1780, 1914? If this was an in-person presentation, I would be polling the audience to see what would be effective in this case. The answer is 1914, but these were specific years. If we gave ranges, we might get different rates that students respond to these different options. Now 900 doesn't seem that crazy, but now it's, oh, okay, well, it's not the 21st century. That's where we're at. It's probably not the 20th. And so what I would expect to see a lot of is the 19th century versus before, where I think I would see more 1451 in this scenario. So the ways that we present these options can be very different. And the ways that we ask the question can be very different. If this was a free response, what do you think you would see? If we just said, in what century was the first multiple choice assessment used? The X century, now we might see some single digit numbers or not. You never know. We could even change the order, and that might make a difference. So we really do have to be careful. This idea of effective distractor, more than 5% of the time, that more might be going on here. And it's important to think about this because, again, we want to be able to detect patterns of student thinking so that we can respond to those patterns. And if a question is able to elicit certain patterns of student thinking, that might make it a better or worse question. Right? If I have a question that doesn't have any other patterns, is it bad? Well, we don't know. So this is how we're trying to get this robust, big picture view in order to try to judge a single item on the assessment based on what we're trying to do with it. So again, for the moment, we're going to just keep these 5% of the time, and later we would deal with maybe more nuanced approach to this. Okay, lots of measures, a lot of math, a lot of numbers thrown at you. So what is it good for? We made a bunch of determinations for each of these measures, but how do we put it all together? So let's look at what it would look like applying this to some assessment. So we're going to apply this methodology of classifying items by measures to all of the college algebra sections at a Southeastern R1 university in fall 2017. So you can see a pretty robust group, about 240 students spread over 9 sections. Most exams were three versions, while the first exam was 2 versions. So we've got a pretty good mix, and you can see most of these were 4-option multiple choice items. So to get started, we did a lot of hard work to get that difficulty discrimination, those estimated item difficulties in those curves. So did it matter? Well, the short answer is yes. You can see this looks more like a normal distribution of scores than this. And in fact, if I have items over here, I can say, oh yeah, these were the hard items. These were the easy items. Whereas it's kind of hard to tell over here. And the same thing, you can see it nice, tightly packed in between -2 and 2. But now we're starting to see outliers, right? Maybe these were too hard compared to all of the other questions. Maybe these were too easy compared to all the other questions. And the same thing here. So you can see here, was this necessary? Yes. And it will give us a good idea on how to classify the assessment as a whole. Does the assessment have items that are kind of distributed across this -2 to 2, or does it have some outlier questions? For the point by zero correlations, we did a lot of work. If you recall, the literature just said use these static bounds of 0.15, 0.2 for these values, and we were actually making bounds that moved based on the number of questions in the assessment and based on the number of students that took it. And did this work? It kind of did. So you can see here, a lot of the questions are in the good range. A lot of the questions, the student's individual response to that question was a pretty good correlation to their overall score, but not always. There were plenty of questions that were not. So are those questions good or bad? We'll need to look at more of the measures in order to make that distinction. But at least our bounds seem to be teasing apart and pulling off some of them to say, look, the point by zero correlations in terms of what we were looking for, in terms of describing the variation for this question over the final or the full exam or full assessment, they weren't ideal. Okay, so what it ends up looking like is we have a bunch of measures and we've color coded them. I'm going to keep the numbers just because we can, but really this model would just care about the colors. So green is that ideal, blue is fine, yellow is a problem. So in a live presentation, I would ask the audience what they wanted to look at, but maybe I'll help focus us along here. Looking at this category, we see one, there aren't a ton of yellows, but it does seem like in these point by zero correlations, we have 2 yellows here. So maybe we'll focus on those. These give 2 very different views of the item. This item, that students, their score doesn't really correlate to their overall score. This was a really hard item versus a really easy item. 21% got this right, 86% got this right. As we saw with those charts, this item difficulty of 10 is massive. So this is a really hard question compared to the rest of the questions. But most importantly, the fit is really good. So these 0.85s are saying this very much fit our model. Students that were really high scoring and this item's difficulty was really high, they were able to get this question right. And the students that were really far away, the students that had low ability estimates with this high item difficulty did not get this right. So this is kind of a good question. This is a question that's going to distinguish your best of the best students, right? The ones that really understand, and it showed not just on this individual item, but how they responded to all of the items in comparison to their classmates. You'll also see it has 3 effective distractors. So this question is showing a collection of thinking across multiple different possibilities. It's not that a student just kind of made a mistake. We see them consistently picking certain options with that 5% expectation. And for the other, these 2 yellows, this outfit and infit, are telling us that this question doesn't fit our model very well. That this has a low difficulty, but students with high ability were getting it wrong. That's what this yellow outfit is telling us. And then the yellow infit is saying, well, for the students that were near that ability, they're not responding as we might expect with that coin flip. So in terms of predictiveness from the model, trying to predict and distinguish between students' ability and just between their final score in this question, this isn't a good question. So you can see here how just having a bad one of these measures isn't quite all of the story. And the way to tease apart these measures are not just, does it have any bad, it's a bad question, but it's about how do they interact with one another. And that was really what the goal of this project is, trying to figure out all of these measures individually, giving some kind of classification individually, and then using those classifications and speaking across them to try to get a holistic idea of what does that say about the question in total. So we could also look at the ones that had 0 effective distractors. They were kind of more consistent. We have them being really high scoring questions, right? Like 97%, there's no chance of getting a response of 5% for any other option because there's not enough percent left. Even though for this 91 there was. So what we're thinking here is the other options that were chosen were more just random choices. The student didn't really try to answer the question. So these are a little bit more tricky. So, well, the individual question really correlates heavily to how they're going to do on the final. The fits are extremely good for outfit. So you can see here, this really fits our model well. Basically, the students with high ability got these all right. The students with low ability, well, they would have needed to get very, very much lower than it in order to not get this right. And so that's kind of the idea here. So overall, these also worked pretty well, even though the effective distractors were 0. But what happens when we collect it by learning objective? I mean, we were saying this entire time that for classroom assessment, we really care about the learning objectives. So when we do that, it's kind of nice that this for a 10, which maybe looked like a problem child because it has 3 yellows, we actually decided, no, it seems to be doing its job, and it's the only one for that learning objective. So maybe that's good or bad. Maybe we want to add an easier question to that learning objective, but still keep that harder question. And conversely, well, we have these 2 super easy ones that are all kind of doing the same thing. Do we need both of those? All right, so we could even use this classification schema to think about, well, what are the questions that you might consider cutting? Where are areas that you might consider adding a question to improve the learning objectives and trying to measure what students are thinking? So overall, the takeaways that we have from this initial classification, because we're nowhere near where we need to be to do everything we want. So the first thing that we saw was clustering it by the learning objectives was actually very useful in trying to talk about overall how the item did, and more importantly, how does that item fit in the entire assessment? Do we need more items of maybe different difficulty or that correlate to students' overall scores more or less with that learning objective? We did a lot of work for this point by zero correlation, and it seemed to pay off that these static boundaries, they're nice, but more nuance is needed in classroom assessment. We also noticed that, I mean, the number of distractors didn't work. So you saw that those zeros didn't really tell us the questions were bad or good. Having a 3 for the distractor, for that one that we looked at, that was a good question, but did that tell us enough? Not really. So we know now we need to add more information, more ways to classify the distractors, maybe like the type of distractor, right? Could we figure out what is this a pattern that students normally think about or not? That would be an important thing to try to pick up. We also wanted to figure out, well, we did this classification as 3 categories. Is that necessary? Do we want to go back to 2 as just a classic binary classification? We use 3 because that's what's in the literature. As we saw, they'll normally say a minimum and then an ideal number. But is this useful? So this is something that we'll look at in the future. And then also we wanted to figure out, well, how could we take all, say, these items and make one item score, right? So it would be an item score by the learning objective. And could we use that to say anything about the students? And could we use that to try to say, yeah, the student got an 80%. Well, what does that mean? Well, I know which learning objectives they actually had the most trouble with, and so I can provide that additional resource immediately, say like in a homework, to have the student prepare and address this deficiency. So those are the kinds of places that we're going with this project. So it's not just a final exams and we want to be able to figure out scores better. But it's really about trying to get to the heart of what does a student know so that we can provide more resources for them directly at what they do or don't know. So if you have questions or comments, feel free to contact me at my Embry-Riddle email. Otherwise, thank you for taking the time to look and listen to our current work on trying to assess assessments.